Let's do a.
Alright, morning. Yeah, okay, so a second reminder that midterm 1 is coming up. It's going to be a week today. Closed book, closed neighbor, at least for the first round. Do bring your IDs with you. And we're going to stay in the lecture room. However, there's going to be seating plan. So I'll tell you where to sit rather than you sitting with you. But it's not that I don't trust you, but it just makes everybody feel a little better. Cheat sheets. I have mixed feelings about cheat sheets, personally. There's an advantage to them because you really put an effort into writing them. And hence, once you're writing it, you're actually learning a lot. But then I feel like a lot of you are spending too much time during the exam on them, right? So I have mixed feelings. So let's ask you guys. I would prefer to do a relatively simpler exam without a cheat sheet, or a relatively harder exam with a cheat sheet. Both sound good and you don't really care. Yeah, exactly. I believe the majority has spoken. Alright, so relatively simpler without a cheat sheet it is. Okay? Relatively to when you had a cheat sheet. Well, the thing is, once you have a cheat sheet, I can't really ask you questions that you can bring with you, right? So that would mean then I have to ask you questions that are more conceptual, and it would mean that you need to think about what you know in order to solve the problem. So hence it'd be a little harder. Okay, so extra office hour on Thursday, just the day before the exam, from 11 to 12:30. I'll be in my office, so just drop by. You don't need an appointment. Since we don't have a lecture on Thursdays and many of you don't have a class on that day, virtual meetings through Skype are available. That's my Skype ID. If you want to schedule a meeting on Skype, please do let me know beforehand, so I can give you a time so I don't have other people dropping by at that time. Sure. Is that a question?
Can you please extend your office hours at least for another 10 minutes? Because lots of people who are sitting here, they're also sitting at 3:22 class, which is exactly the same time. So
if I go which way it would resolve the problem? To 1 or from 10:30 to 1? 1? Sure.
Yeah.
Okay, so your SQL Plus accounts are now ready. All of you guys eager to do some SQL, now you do have the chance. If you want information on how you can connect to your SQL accounts, there's some information here. Go through this and hopefully this will help you. If you want to have some databases to play around with, if you go on this link, here you can find all that SQL. This is the examples that I'm using in class mostly are coming from these tables and these databases. So you can put those onto your MySQL, and you can Oracle Server or MySQL, and so you have a chance to play around with the examples as well. Pei is coming to all the tutorials, and he's not the main person doing the actual tutorial, so he's coming as to help everybody. So if you have any questions regarding how to connect to your SQL Plus account, do talk to Pei during your tutorials as well, and he can help you. Group projects. Team member issues can be complex, and I do know that. Among the first few things that you need to figure out between your team is what language are you going to use and what relational database you're going to use. Okay, so whether you prefer to do PHP or Java, or whether you prefer to do MySQL or SQL Plus on Oracle Server. And the way we have it set up is that at the end of the semester, you'll all have the opportunity to give feedback on the other peers in your group. So we're going to have a peer evaluation at the end of the semester. However, it's not really going to help if someone is not participating right now and for you to let me know at the end of the semester. So if you're having serious issues with a team member, that they're not showing up to your meetings or they're not really participating, please let me know. Right now I can talk to all of you and figure something out. There's not much I can do at the end of the semester, other than not give them the mark, which doesn't really help you guys. Alright, so if you're having major issues, let me know. Any questions before we start? Alright, so where were we? Databases allow you to say one attribute determines another, and they call these functional dependencies. We introduced some rules that allow you to derive implicit dependencies based on some explicit ones that you already know. But that was too painful. Going through the proof and proving that this is something else that you can do using 5 rules that we looked at. So we introduced attribute closure. And with attribute closure, what you do is you try to find all the things that could be found based on the set of starting attributes that you have. Functional dependencies, if you have them in a table, they introduce anomalies such as update, insert, and delete anomalies. And the main reason why we're going through all this pain is to reduce and omit those anomalies. And we saw that the solution was to decompose our tables. Okay, so if you have a big table which has a bunch of functional dependencies, we need to decompose it to get rid of those anomalies. If we decompose randomly, we might get lossy joins, which means that when you decompose and put things back together, you get things which never existed. So now your name is going with someone else's grade, and who knows where it's going to end up. Normal forms are going to allow us to have lossless joins. So when we decompose and we put things back together, we're sure that we didn't create anything bogus. And we finished off with looking at 2 examples on BCNF. What we're going to do today is mostly go through examples on BCNF, minimal cover, and third normal form. So if you're sitting on your own or if there's no one around you, please do move close to someone else because we're going to be doing a lot of teamwork today. Okay, so remember BCNF definition? For all non-trivial functional dependencies of the form a bunch of attributes x giving you b, x must be a superkey. Okay, so this is a relation a, b, c, d, and these are the functional dependencies that I have. B gives you c and d gives you a. Finding the closure of a will just give you a. Finding the closure of b, that's going to give you b and c. Closure of c is giving you just c, and closure of d is giving you a and d. B and D, the closure of B and D is going to give you A, B, C, D. So that's going to be the only key that you have here. And now we're going to start looking at the functional dependencies. There's a functional dependency B to C, and now we're going to check if B is a superkey. The reason why I put all the closures at the top here at the beginning is that once I have all those closures, it's easier for me to find the answers for the rest of the questions that I'm going to ask. Right? So now that I have all these closures, it's easy for me to see that B is not a superkey because it's not, it's only finding B and C. So it's not, we decompose based on the golden rule. So now we're going to take this and decompose it into 2 tables. X, which is the left-hand side, it is going to be B. B is our right-hand side is C, so B and C is going to go into 1 table, and the rest, AD plus X plus B is going to be my second table. So now I have 2 relations instead of R. I have R1, which is BC, and R2, which is ABD. Now I look at these 2 again. R1 I don't need to worry about anymore because it's only 2 attributes, and everything with 2 attributes is in BCNF. However, when I look at R2, R2 is still not in BCNF. There's a rule that D determines A, which is violating BCNF. Is D, we have to check whether D is a key for this relation. D is not a key for this relation, so I'm going to further decompose this to have D8 in one table and BD in another table. And at the end, we're going to have R1, R3, and R4 as 3 different tables. The second example we looked at was a little bit more confusing. So these are the two examples we covered at the end of the previous lecture. So that's why we're going pretty quickly over them. So this one, we'll start out by finding the closure of AB plus. That gives you ABC, and D, closure of D is going to give you D and E. The relation is not in BCNF, so we need to decompose. AB is not a key because it's not finding ABCDE. So based on this rule, which is currently violating BCNF, I'm going to decompose. I'm going to have one table which is ABC, the other which is ABDE. Okay, so ABC now looks good. AB is a key for R1, that's not a problem. However, D is not a key for R2. So R2 is ABDE and the closure of D is DE. So it's still not a key for here, so I need to decompose. D and E, I put these into one table, and ABD I put in another table. Now the question is, do I need to decompose ABD any further, or it's already in BCNF? And if you look at this, and if you look at AB, AB is not a key for R3, right? Because AB only finds A, B, and C. And I have D here, so AB is not a key. However, this functional dependency is not really going to be troubling me in this R3. This functional dependency means that if I know A and B, then C is going to be redundant. If I have multiple values for C, that's going to be redundant. However, I don't have the attribute C in this table. So the part that is actually troublesome is not part of my table. So although AB is not a key for here, but since this functional dependency doesn't hold in all three, we're not going to decompose this any further. Any questions about that? So the question is, how do we know whether something is a functional dependency holds in a table or whether it doesn't hold? So what we're going to do is we're going to take the closure of all of the our attributes based on all of the functional dependencies. And then what I'm going to do is we're going to check to see for a functional dependency X determining B in a relation S. First of all, we're going to check to see whether all of these are contained in S or not. So first I'm going to check to make sure all these attributes do exist in that table. If they all do, then I'm going to find the closure to see whether that is a functional, whether the key is holding or not. So let's see whether AB determining D as a functional dependency holds in this functional dependency when we look at S. Okay, so the relation is R, which has A, B, C, D, E, and these are my functional dependencies. Now once we move into S with A, B, C, D, does A, B determining D hold or not? Okay, so that's what we're trying to see. First we're going to check if A, B, and D are all present in S. S has all three, so yes they are. Now I'm going to check to find the closure of AB plus. So the closure of AB is going to be, let's see, so AB gives you C. So now you have ABC. BC gives you D. Now you have ABCD. CD gives you E, so now you have ABCDE. So since the closure contains everything, and it also contains D, then AB determining D does hold in S. Okay, so if I was to decompose R into multiple relationships, and I was considering S, I had to consider this functional dependency because this functional dependency holds in my relation S. What about this one? CD determining E, does this one hold? Well, I'm going to check here, and E is not part of this relation. Since E is not part of this relation, I don't really need to worry about this one because it's not going to hold in this relation. Okay, so 2 steps. First, make sure that all the attributes that are part of your functional dependencies are present in your table. And then make sure that what's showing on the right-hand side is within the closure of what's in the left-hand side. Any questions? Quicker questions. Do this one on your own, please. Few more seconds. Alright, this one needs quite a bit of discussion. Talk it over with your neighbors.
Succeeding.
Right, a few more seconds. Okay, 5, 4, 3, 2, 1. Random clicks. Right, so 82.3 is the number for today. Okay, so second round, this is what you think. First round, this is what you think. Let's see. Okay, first let's look at A. So, if you want to find the closure of A does not determine anything other than itself. So closure of A is just A. So since A does not determine B, that dependency is not, that functional dependency does not hold in S. But first of all, I checked and I saw both A and B are part of S, right? So they're both part of S, that part is okay. But since B is not in the closure of A, then it's not going to be true. A, B determines E. S does not contain E, so this functional dependency cannot hold in S. E determines B, again, since E is not part of that, it's not going to hold. D is saying BCD determines A. A, B, C, D are all part of S, so that part is fine. Now I need to find the closure of BCD. And if you find the closure of BCD, BC gives you D, BCD, CD gives you E, DE gives you A, so it gives you everything. So yes, that functional dependency holds. Question? At the back, yeah.
But E isn't in S, so that doesn't matter for E?
So you mean for the closure of BCD?
Yeah.
So that closure BCD does determine E. However, E is not part of S. That's not a problem. So although it could be found, but it's not part of S. If I said BCD determines E instead of A, that would have been problematic, and I would have said that does not hold because E is not part of S. The reason why you gotta add E is because you need E in order to determine A, right? If you don't consider E, then you cannot get to A. So E gives you this, so E allows you to have A, but E is not itself part of this relation, but that is fine. Does that answer your question? Instead of BCD, just BC? No. Since closure of BC would be the same, then yes, that would hold. Because with BC you can find D. Can I get your name?
Justin.
Justin? Thanks. Anyone else? Yes?
I'm a little bit confused. I thought A would give you C and C with it as well. Like you can do B, C, and you get B, and then you get
So
C, then you get E.
So which one? Which answer are you discussing?
A little bit confused about why B doesn't work.
So the question is, why isn't B right? So if we go back to here, first we check what are the three values. All of the values that are in that functional dependency are part of the relation that we're talking about, right? So for B, I have A, B, and E, but in my relation S that I'm projecting to, there's no E. Isn't it the same for D? Well, D is talking about B, C, D, and A, and all four of those are present in S. So what you need is everything in that functional dependency has to be part of the relation that you're talking about. For B, E is in there. For D, everything is there. Yeah.
Wouldn't you need to use the
Let's do an example because this seems to be confusing everyone. So let's say this is my table, and let's say I have E, B, C, D, and E. Now, E is here, so I can, based on this E, I can come up with value. So let's see which one it is. So D and E together gives me A, right? So in the closure of my BCD, I can get to A because I have knowledge in this E. Now later what I'm going to do is, I'm going to take this E out of here, right? So I have information about this E, it's just that I'm not adding it to my relation. So any closure that I can find based on E, I'm still going to add to my closure because I know what this value is. It's just that I'm going to omit it later. So to get to A, I can use this E, and that's fine. But now in this new relation, if I want to check whether A, B determines E exists, I don't have that E anymore to check it. I do have it, but it's not my concern anymore because I've gotten rid of it in this table. If this is the table that I'm keeping now, if there's a redundancy based on A, B determining E, since I'm not keeping that here anymore, I'm not really worried about that. I know it's a little confusing, but think of this as knowledge that you can use, but you're not really worried about any redundancy in it because you're not going to store it as part of your S. Any other questions? Okay, so for the two questions, for the two examples that we just looked at, what we were doing is we were looking at the functional dependencies at the top, and based on those we were making a decision whether something is violating BCNF or whether it's not violating. However, we've already talked about implicit functional dependencies as well, right? I have a bunch of functional dependencies which are being given to me explicitly, but based on those I can derive new ones. And implicit functional dependencies, believe it or not, are just as important as the explicit ones that are being given to us. So when we're looking at functional dependencies and making sure nothing is being violated, we need to take those implicit functional dependencies also into consideration. Okay, so why don't you give this one a go? So this is the relation, and these are the functional dependencies. You want to see whether this is in BCNF or not. If it's not, you want to decompose it, and then we'll discuss it together. Okay, please do work with your neighbors on these. I do want you to talk them over, so in case you're on the wrong track, you can help each other as well.
implied by the explicit ones? Two of the things get right. Yeah.
Why you couldn't use these? Because what do you mean by couldn't use these? Or does it hold over this table? Saying these are the entities and person, these are the attributes that hold over the field. But you just had a table S. And that's just one table within your entities. So it's saying, it's saying, does A, it's not saying does A, B, and E hold in general, because in general, yes, it does. It's just saying does it hold over this table, this particular smaller table. Yeah, so I say it has worked over that table, but it doesn't in general. Yeah, so
I don't really even understand the question to ask.
it says holding, and it's not hold over the whole database. It's for in general. So we're just practicing how to do it. Because it's applied, because in the next section, 3NF is a different kind of decomposition that relies on us being able to do this. Oh yeah, for BCNF.
I think it's similar to that. So you just like
It's completely
start off with like
yeah, so you know that so it's just a way of decomposing tables to get rid of that. There's just a process, yes. And it's a fight after the process is
sometimes you might have to go around that several times.
that's after you go through the process that you're able to so we're just getting
Okay, can you just click whenever you finish so I know how many of you we're waiting for?
That's one. Then you just figure out what
So are we just asking to we just ask if
So, what does it mean for it would be BCNF and it's not violent. Yeah, I know what I read. So if you have a functional where exit okay. That means that
so I look at the functional defenses that I'm given and I ask each of those is
then this is violated.
I ended up with ABC and one table. So I ended up
Yeah. Well, sometimes it just so both you nowadays it's once you pick everything what you get
that table R is so we have functional dependency.
you know that functional dependency
It's better to use So that means I need
so in R3 there's no optional sentence.
Right, so you're clicking if you finished. Are we still waiting for anyone? Alright, let's look at it together. So your answer might be different to mine because depending on the order in which you look at the functional dependencies, you might get different answers. So this is one possible answer. Okay, so the functional dependencies that I have is A determines B, D determines F, and B determines C. And just a reminder that we're also talking about implicit functional dependencies here. Okay, so do watch out for that. So first of all, I'm going to look at the left-hand sides of everything here. I'm going to find their closures. So closure of A is ABC. A gives you B and B gives you C, so the closure is ABC. The closure of B is just B and C. And closure of DE is DEF. So far so good? Okay, so now let's have a look at A determining B. A is not a key for R. And I have A determining B, so this is violating BCNF in R. So I'm going to decompose it based on the rule. A, B goes into one table, and A, C, D, E, F is going to go in as a second table. R1 is not good because I only have two attributes, so that's in BCNF. I don't really need to think about it anymore. R2 has A, C, D, E, F, and I need to see whether this is in BCNF or not. So the steps that I need to do when I'm checking something is in BCNF or not. First of all, I'm going to find all the functional dependencies that hold in this relation. So, this one does not hold in this relation because I don't have B here anymore. D, E, F, that one does hold here. And this one doesn't hold because I don't have B again. Okay, so this one could probably be problematic. Now here, when I look at this, DE is not a key because DE, the closure of that just gives you DE and F. So since DE is not a key, is not a super key, then I need to decompose. I'm going to decompose it down to DEF, so that's going to go into one table, and I have ACDE, which goes in the second table. R3, if you look at that, I have the functional dependency that holds here is DE giving you F. DE is a key for this relation R3, so R3 is in good shape. It's in BCNF. Now the question is R4 in BCNF? Does anyone have an answer? Yeah.
I think no, because A is able to determine C because it's an infinite attribute.
So yeah, exactly. So the problem here is, if you just look at these functional dependencies that you have here, R4 seems to be in good shape. So I'm going to look at this one. A determines B, doesn't hold here, so that's fine. DEF doesn't hold here, that's fine. And BC doesn't hold here, that's fine. So you might think, just by looking at these functional dependencies, that it looks good. However, do look at the closures when you're going through this kind of questions. The closure of A is telling you that A determines A determines B, and A determines C. So what that means is that since the closure of A has all of those, that means that A determines B, and also A determines C. How can I get A determines C? You have A gives you B, B gives you C. By transitivity, you can get A gives you C. This A gives you C is something that we also need to consider. Now, if you look at that in R4, we have a functional dependency that says A gives you C. Is A key, a super key for R4? The closure of A is just A, B, C, and is not, so D is not part of that. So A is not a key for R4. Therefore, I need to further decompose. So now, since the closure of A contains C, we're going to have the implicit functional dependency A gives you C. So we're going to decompose R4 into A and C and D, A. Now these are the two new tables that we have. So at the end, the final answer is going to be R1, R3, R5, and R6. Finding all the implicit functional dependencies are tricky, so that's why we look at the closures, right? Even if you couldn't see this based on transitivity, just by finding the closure of A, which gives you A, B, and C, you would already know that this is going to hold inside this table. Okay, so I encourage you that whenever you're looking at the functional dependencies, make sure that you're also checking the closures as well. Question?
There's another way of doing this. I mean, absolutely totally different way, so we can do it in two ways and by the end compare it to results.
Unfortunately, some of the algorithms that we're looking at, there's no easy way of doing them. So if you look at, most of these are NP-complete problems that we're looking at. So even when you're doing it algorithmically, the easiest way, it's a brute force algorithm usually. That's why we're not going to give you really a hard time in your exams usually with really big questions. But I think if you look at the closures and the functional dependencies, and at the end look at all of the tables that you have, you can validate whether what you have is correct or not. So once you have the final answer, you can go through your tables, your relations, R1, R3, R5, and R6, one more time, check them with all the closures and make sure there's nothing that's violating them. So I would say that's the second way of doing it, validating everything afterwards. Any questions? Right, let's do one last BCNF. Okay, so I'm doing quite a bit of examples because that's the only way you would understand them. There's no point in me just covering it without you trying them out yourself. Okay, just click whenever you feel like you're done.
So you don't have to look at
Next, see whether your answer is up there. Okay, so if you're not already discussing it, please feel free to talk to your neighbors as well.
Yeah, but C doesn't give you B. If C doesn't give you B, C just B. But if B and C together, you need both. Get them all yeah, it means B, C together. So you need both.
Right, 5, 4, 3, 2, 1. Random clicks. Okay, so let's see. So what I'm going to do again is based on the functional dependencies that I have, A on the left hand side, C, AB, and BC. Let's find closures. Closure of A is going to be AB. Closure of C is going to be CD. Closure of AD is going to be AD itself. You can get also C, and you can also get B. and closure of BC is going to be BCAD. Now AB is violating BCNF, so we need to decompose. AB is violating this because A is not a key. So we're going to decompose it into AB and CDA. R1 is now in good shape. R2, we need to see which functional dependencies hold. And you can see that CD still holds in this functional dependency, because both C and D are in this relation, and the closure of C contains D. So CD is violating, so we need to decompose. We'll put CD in one table and AC in another table. So at the end I'm going to have R1, AB, R3, AC, and R4, CD as the right answer, which is B. Okay, so good work. The majority of you got that right. Random clicks tend to be on C, because everybody who randomly clicked at the end pressed on C. Any questions? So, if we use our very sophisticated algorithm, you get A, B, A, C, and C, D as the right answer. But you can also randomly come up with values like A, which says A, B, A, C, and B, D, which also seems to be in good shape. But if you try it out, we're going to get the bogus tuple that we've been talking about. So if you use option A in order to decompose, and then join back together, you're going to get this 1, 2, 3, 4, which was never part of your relation. Any questions? Okay, so this BCNF stuff is great. Well, we have one easy algorithm that you take relations and functional dependencies with it, and you transform from a database which has a bunch of redundancies and anomalies into one which doesn't have any. So what's the problem with BCNF? And I bet all of you are like, problems? We just spend all this time learning this algorithm. Please don't tell me there are any problems, and we need to learn more algorithms. Unfortunately, we do, because BCNF does not preserve dependencies. And again, you're like, what the hell are dependencies that are not being preserved? So let's have a look at an example. So in this example, let's say these are the two functional dependencies that we have. We have unit, we have company, we have product, and the two functional dependencies says unit gives you company, and company and product gives you unit. Okay, so is unit a key? Let's see, the closure of unit is just unit and company, doesn't have product in it. So no, unit is not a key here. So I need to decompose this. Right? Based on BCNF that we've done so far, I need to take this table and put it into unit and company, and also unit and product. Okay, so this is what we've been doing so far. Whenever we see a violation in BCNF, we're going to put it into two different tables in order to avoid redundancy. And you're right, we should do this, because since unit determines company, that means in this table we might have redundancy. If the same unit is happening multiple times with different products, then we're going to get the same value for the company as a redundancy. What's the problem though? This all seems to be great, but while decomposing into BCNF, I kind of lost this information. In this table, I can make sure that unit always determines company, but how can I make sure that this is correct? So let's say, let's put values into this. So let's say that when we decompose, we get values that are fine, right? Here, Unit is determining company, so there's nothing violating here. And I don't have any functional dependencies for this table. So yeah, nothing seems to be violating. But when I merge these two back together, I've decomposed. When I merge back together, I don't get any bogus tuples, right? Because I've done BCNF. So I'm not going to get any bogus tuples. But what I'm going to get is that when I put these back together, I'm violating one of the functional dependencies that I had. Why was I missing that? Because I didn't have any table, any one table that was showing me the information on all company, product, and unit, so I could look at that and see, there's where I'm violating this dependency. Does anyone have a question about the example? Right, so it's important to see that although BCNF helps you with avoiding redundancy, but it's giving you another problem, which is now it's hard for me to check whether a few of these functional dependencies hold or not. How could I check whether this is true or not? If I am using BCNF in my tables, then every time you want to add something to either of these two tables, what I'm going to ask the database management system to do is to join these two tables and to make sure that this doesn't happen. Which is doable, but costly. Okay, so whenever I have to make big joins, especially if I have millions of tuples in each of my tables, whenever I need to join to make sure that one of my functional dependencies is not being violated, that's usually costly. So 3NF comes to the rescue. And it seems like a good time to take an early break. Let's take a 10 minutes break. Let's resume at 10 past, and I'll tell you all about 3NF.